We are now to the video. No more readiness. You are as ready as can be. We are going to solve counting problems with generating functions. I will continue forward, assuming that you have watched videos 8.4.1 through 8.4.4. In the remainder of the videos for section 8.4, I have included this table. This is just a good reference to come back to decide how to write a summation, what the representation is, how to find the coefficient, and so forth. So we will use this as we are working through the rest of the examples. For our first question, I want you to notice that I already have a solution up there, but that solution was not found using generating functions. So the point of that is just to point out to you that you don't have to use generating functions to solve these, but it is one method that you can use, and you can also use the linear equation model. So I will assume that you've already learned how to use the linear equation model, and I'm just going to talk through it very quickly. If we have a situation like this where we have 20 identical balls, 5 boxes, and each box must have more than one ball, I originally model it with 5 variables, x1 through x5, equal to 20 because that's how many balls we are distributing. Then we say each box must have more than one ball. So for every box, it has to be greater than or equal to 2. More than 1 is greater than or equal to 2. So I would subtract 2, which means I'm actually subtracting 10 from the right. That gives me my new linear equation, x1 prime plus x2 prime and so on is equal to 10. Using the combinations with repetition model, that gives me 5 choose 10, or 5 plus 10 minus 1 choose 10, which is 14 choose 10. This is my correct solution. Now let's take a look if we can find that solution again, but using generating functions. So keep in mind that I'm looking for 20 identical balls, so that means x20 of g of x. So what's x20? What is g of x? x20 g of x means that I'm doing x20, and then let's think about what g of x is. G of x would be each box would be represented by, since they each have to have more than one ball, x squared plus x cubed plus x to the fourth and so on. Now, there is no upper bound. So this says at least 2, but it doesn't have an upper bound. So I'm going to keep it infinite because they're so much easier to work with. So that means I have x squared plus x cubed plus x to the fourth and so on. And I have that 5 times because all 5 boxes have the exact same restrictions. From here, what I want to do is take out an x squared, because what I really want is to always be able to write it as x to the 0 plus x to the first and so on, because this is the fundamental identity. So how would I do that? Well, I would take out x squared, except I'm doing it 5 times. So what I actually have, oops, didn't mean to switch colors there. What I actually have is x to the 20 still, and then I've got x to the 10th out because I took out x squared, but I took it out 5 times, so that's 10 total x's. And that leaves me with x0 plus x1 plus x2 and so on to the 5th power. So again, 10 times 5 gave me, 2 times 5 gave me the 10. Now this part's a little bit new. We haven't done this yet. I want to take a look at the fact that I'm trying to find the variable or the coefficient for when x is to the 20th power. But I now have a 10 that I have factored out. So essentially what I'm going to do is I'm going to divide by x to the 10th. Well, that means what I'm going to be left with here is 20 minus 10, or x to the 10th. And then what I have left over here is still x0, x1, and so on. But x0, x1, and so on, recall, is the fundamental identity. This is 1 over 1 minus x to the 5th. So far we're doing great. The last thing I'm going to do before actually solving is I'm just going to rewrite this as 1 minus x to the -5th. And you'll see that that's going to make things easier as we move forward through this. So what does this tell me my solution is? Well, remember, I'm trying to find x to the 10th. I'm trying to find the coefficient for when x is to the 10th power. This tells me that this is n, 10 is k, and so to find x to the 10th, I'm taking -5, choose 10, and then if you'll recall, that's, and then of course negative x, oops, -10, negative x to the 10th power. So, and I'm actually going to write that in a different color again because this part gets real complicated sometimes. So the -5 choose 10 can be rewritten as 5 plus 10 minus 1, which is 14 choose 10. And then I get -1 to the 10th. The part that I've written in blue is rewritten as obviously -1 to the 10th and x to the 10th. And do I really care about the x to the 10th? No, I sure don't. Because remember, that's just telling me that that's going to be, the variable is x to the 10th, but I want the coefficient. So what's my final solution? Well, x to the 10th just tells me it's x to the 10th. -1 to the 10th is +1, and this is +1, so I'm going to cancel them out. So what's my final solution? It's 14 choose 10. Did I get the same solution? Yes, I did. These two match up, so I feel pretty good about myself that I've done it right twice. Let's look at the same question, but with an extra restriction. So instead of just more than 1 in each of the boxes, we now have more than 1, but no more than 10. So essentially what we're saying is that 2 is less than or equal to x of I is less than or equal to 10. And that's for all 5 of the boxes. Now I did this one with the principle of inclusion-exclusion, as well as obviously we're going to work through with generating functions. But using the principle of inclusion-exclusion, we would start the exact same way we started before, and we would subtract 2 from each one, which is exactly what we did before. The only thing different here is because I had an upper bound, by subtracting 2, that leaves me with limits from 0 to 8 instead of 2 to 10. So just as I did in the previous question, I ended up with combinations with repetition of 5 choose 10, and that gave me 14 choose 10. So if you'll recall, this was actually our solution to the last question. Now, it's a little bit harder because now I have to figure out how to tackle the restriction of 0 is less than or equal to x of I is less than or equal to 8. So I'm looking at that 8. So what am I going to do there? Well, I know that if I let a condition be that x of I is greater than or equal to 9, then not meeting that condition means x is less than or equal to 8, which is what I want. So what I do is I look at the fact that there's 5 conditions, and I'm going to choose one of them. So 5 choose 1. Then I'm going to assume that the condition is met for just one, which means I'm going to take this equation and I'm going to subtract 9 from each side, just for one of the variables, because only one condition is being met. That leaves me with x1 double prime and then x2 prime, x3 prime, etc. is equal to 1. That linear equation model gets rewritten as 5 choose 1 combinations with repetition model. So 5 boxes with just one item left to, distribute. That gives me 5 choose 1, and then this is 5 plus 1 minus 1 choose 1, which is 5 choose 1. So my final solution is 14 choose 10 minus 5 choose 1, 5 choose 1, or 14 choose 10, and then 5 choose 1 is 5, and 5 choose 1 is 5, so minus 25, or I could say 5 squared, whatever makes most sense to you. I would probably leave it just like this. So now let's look at how we can write that or solve for that using the linear equation model. I'm still using 20, and you'll find that many of these steps are going to look identical to what we just did. So that's going to tell me that I'm finding the coefficient when x is 20, and when I write the generating function, I start with x squared just as I did before, but this time I have an upper bound of 10, and then still to the 5th power. So just as I did before, I'm going to factor out x squared 5 times. So x to the 10th, and that leaves me with x0 plus x1, and so on. Oops. But now the upper bound is x to the 8th, because I factored out 2. Just as I did in the last question, I'm going to divide by x to the 10th, so that's going to give me 20 minus 10, or 10 here. And then this part's a little bit different because this is not the fundamental identity anymore. Now it is the finite geometric series. So I'm going to rewrite this as 1 minus x to the n plus 1, so 8 plus 1 is 9, divided by 1 minus x, all to the 5th. And my very last step before I actually do some things that we haven't done before is to rewrite as 1 minus x to the 9th to the 5th, and 1 minus x to the 5th. Now, this is where things are going to get a little bit more complicated. So what I want to do before I do convolution, which is something we've never done, what I want to do is I just want to be clear about what a sub n would be for both of these different functions that I have, because I have 2 functions. I've got 1 minus x to the 9th to the 5th, and I've got 1 minus x to the, oh sorry, that should be negative 5, because obviously it's denominator. So what am I going to do? I want to take a look at a sub n. Now, where am I going to come up with these? Well, remember when we started this video, I gave you a table and said, here's a bunch of stuff we've learned already. This is a really good resource to look back at. This is when I might look back at that. How am I going to write a sub n for 1 minus x to the nth, 1 minus x to the 9th to the 5th power? Well, a sub n is going to be 5, choose k, and then negative 1 to the k, because we have negative x here, so negative 1 to the k. Then I have for my other function, and we're going to call the blue one h of x. And then my other function, we'll just call it f of x. And a sub n is going to be found by, because it's a negative 5, so it's negative 5, choose k, and then that's going to give me a negative 1 to the k as well. So let's go ahead and take a look. Now keep in mind that what's going to happen here, if you'll recall, is I'm going to get negative 5 plus k minus 1, choose k, and that's going to give me a negative 1 to the k as well. So really what's going to happen is I'm going to get a negative 1 to the k as part of this, and a negative 1 to the k because it's negative x, and those two are going to end up canceling out. So for simplicity's sake, I'm going to stick with just negative 5, choose k. So now we come to what is called convolution. And this is how we're going to solve for x to the 10th. So what I need is I need the sum of the exponents to be 10. And then I'm looking for whatever a sub n is for that. So I'm going to break it into cases. Case 1 is, remember, I need a sum of 10. So case 1 says, what if I don't use anything from h of x? So I get 0 from h of x, which means I have to get all 10 from f of x. Let me rewrite that, 10 from f of x. Well, that would be, of course, that k here would be 0, and k here would be 10. So before I do that, I want to look at another case. Case 2 says that I'm going to get, this is 9 at a time. Whoops, I just made that look really messy. So every time I choose h of x, I get 9 x's. So that means I get 9 from h of x, which means just 1 from f of x. Now, is there a case 3? Well, case 3 would be that I get 9 times 2, or 18 from h of x, but I only need 10. So there is no case 3. I'm all done. These are my cases. Now, k here is not 9. K here is 1 because I'm just using one of these, and one of those gives me 9 x's. And then k here is 1. So now let's take a look at how we can use this to find our solution. So if I use k of 0 for h of x, that's going to give me 5 choose 0, negative 1 to the 0. And from f of x, k is 10, is going to give me negative 5 choose 10. And then remember, it was negative 1 to the 10th, negative 1 to the 10th. And those negative 1 to the 10ths would cancel, and 5 choose 0 is actually 1, and negative 1 to the 0 is 1. So if I simplify this, this gives me just the negative 5 choose 10, which is 5 plus 10 minus 1, or 14 choose 10. If I look at case 2, that's 9 from h of x. So for h of x, where k is 1, I get 5 choose 1, negative 1 to the 1, and then 1 from f of x gives me negative 5 choose 1, and then again, negative 1 to the first, negative 1 to the first. So simplifying that one, 5 choose 1, and then negative 1 to the first is negative 1, so I'm just going to write that as minus. And then this guy is negative 5 choose 1, which is 5 plus 1 minus 1 choose 1, which is 5 choose 1. So what's our solution? Our solution is adding all of this together. And guess what that gives us? 14 choose 10 minus 5 choose 1, 5 choose 1. Same solution. So I absolutely detest when my videos go over 20 minutes, but unfortunately I really feel like you need another practice of both types of questions. So I did include another practice. You will be here past 20 minutes, but try them both and then press play to see how you did. So what we're dealing with is 24 identical robots, 4 assembly lines. The first one has a restriction of at least 3 robots to the line. So x of I is greater than or equal to 3, which means I'm going to use, x to the 24th of g of x, where g of x is going to be modeled using 4 assembly lines, and they all have to have at least 3. So it's x cubed plus x to the 4th, and so on. No upper limit, but all 4 assembly lines are the same. Now, just as I did before, I want to factor out so that I have x to the 0 here. So I'm going to take out 3, but 4 times. So x to the 12th, and that leaves me with x to the 0 plus x to the 1st, and so on, still to the 4th power. I'm going to subtract 24 minus 12. That gives me x to the 12th. And then I'm going to replace all of this with the fundamental identity, 1 over 1 minus x to the 4th. And then I'm just going to rewrite that as x to the 12th and then 1 minus x to the negative 4th. So from here, I'm now just trying to find x of 12, right? So how do I find x of 12? Well, again, what we did on the last example is I went ahead and was specific about a sub n is going to be -4, choose k, and then I'm going to have -1 to the k and -1 to the k. And you can do that. I find it especially helpful when you're working with convolution. With this one, it's not as important, but of course, that is where I'm going to come up with my solution. In this case, I've got, let me switch back colors again and move this down so we have room. This is x12, and it's going to be -4, choose k, which is 12, and then -1 to the 12th, -1 to the 12th, which I mean, you can write or not write, honestly, as long as you remember that they were there. Well, what's -4 to the 12th? I'm sorry, -4 choose 12. It's 4 plus 12 minus 1, or 15. Choose 12. So that's the final solution for the first question. 15, choose 12. Now, how am I going to find the second solution? So notice it has at least 3 is less than or equal to xi, but no more than 9. So from 3 to 9. So how is that going to change things? Well, I'm still going to have x to the 24th of g of x, and this time my g of x is going to be limited, right? It's going to have an upper bound. So this is x cubed plus x to the 4th all the way up to x to the 9th, and this is still to the 4th power. Then I'm going to factor out the 12 just as I did before. So I'm factoring out 3 4 times, which is 12, which leaves me with x to the 0 plus x to the 1st, all the way up because I factored out 3. The upper bound is now x to the 6th, still to the 4th power. That's going to give me 24 minus 12, or x to the 12th. And then this is a finite geometric series, so now it's going to look a little different. It's going to be 1 minus x to the 6 plus 1, or 7, over 1 minus x. And that gives me 1 minus x to the 7th, whoops, I forgot to the 4th power, to the 4th, and 1 minus x to the -4. So now I'm kind of at the point where I was before when I said, okay, let's do convolution. And again, if it makes the most sense to you, and quite often it does, let's call this first one h of x. And I know that to find my a sub n of that particular function, I'm going to take 4 choose k, -1 to the k. And for my other one, we'll call it f of x, I'm going to take -4 choose k, and then I'm going to end up with -1 to the k twice, which is going to cancel out. So I'm going to leave it just like that. So now what? Well, now it's convolution. Case 1. Keeping in mind I'm looking for a total of 12. I can get 0 from h of x, which means I get 12 from f of x, because that would add up to 12. Case 2, remember h of x comes in groups of 7, so 7 from h of x, which leaves 5 left over from f of x. And then there is no case 3 again, because again, if I have 7 twice, that's 14, and I'm looking for a total of 12. So let's look at how I'm going to model 0 from h of x. That would be 4 choose 0, -1 to the 0, and then 12 from f of x would be -4 choose 12. Well, 4 choose 0 is 1. Negative 1 to the 0 is 1. Negative 4 choose 12 gives me 4 plus 12, or 16, minus 1, which is 15. Choose 12. Now, case 2 says I have 7 from h of x. So remember, that means k is 1 because I'm taking 7 at a time. So this is 4 choose 1, negative 1 to the 1. And then 5 from f of x, I'm using negative 4 choose k, so that's negative 4 choose 5. Simplifying that one, 4 choose 1, and then the negative 1 to the first. So I'm just going to write negative 4 choose 1. And then negative 4 choose 5 is 4 plus 5, or 9, minus 1, which is 8. 8 choose 5. So what is my final solution? My final solution is adding what I've written in white together. So 15 choose 12. And then I'm adding a negative, so basically I'm subtracting 4 choose 1, 8 choose 5. And again, I don't need for you to multiply that out and find the solution. I think you can leave it just like this and be perfectly happy that you did a great job. I wanted to look back at this question one more time. This is where I'm going to leave this one for you. Convolution would take a really long time, so I'm going to let you try to figure out how to solve this. But I've written each generating function and then how to find a sub n for each one, and then I'll let you figure out how to move forward from there. You can certainly do convolution, or you can approach it in a different way. Coming up next, we want to take a look at how to find the explicit form of a generating function, and that will continue as we look at the last video, which is solving recurrence relations with generating functions. But this next video will give you good practice before you learn something new in using generating functions with recurrence relations.